Okay, let's start. So last time we introduced a new type of memory technology called phase change memory. It uses some material called phase change material to record the data. The material can achieve high resistance and low resistance. And by the high resistance and the low resistance, we can record 0 and 1. And the transition between high resistance and the low resistance can be enabled by a set operation and a reset operation. So here is a example of the memory array. It's very similar to the DRAM, to the SRAM. The difference is the cell itself. We just use a phase change memory cell to replace the capacitor of the DRAM. And in the middle of the cell, there is a thin layer of phase change material. And this is a heater. By a long duration, by the short amplitude current, we can program the cell into crystalline state, which is the low resistance state. It can record a 1. By a short duration, but a large amplitude current, we can program the cell into a morpher state. It has a high resistance. We can use it to represent a 0. So there is a huge resistant spectrum between the low and the high resistance. It's possible to have more states in the middle of this range. How can you achieve that? It's easy. You just program a crystalline state and then generate some, you just create a morpher state. This is a morpher state. You just create some crystalline filaments on the morpher fraction. In this way, you can have 10K ohm, 1 amp ohm. By these resistance states, you can record more than 1 bit in one cell. But again, in order to generate this crystalline filaments, you need to write more because all of these curves are generated by writes. By more writes, the endurance decreases, and more power consumption is consumed by these writes. So there is another very interesting characteristic of the cell. The phase change material is actually a chemical alloy. You have tellurium, germanium, and antimony. The distribution of these elements in the alloy is not uniform. Some portion has more antimony. When you do the programming, when you try to create some filaments on the morpher fraction, if the filaments has less antimony, it's slower. If you have more antimony, then it's faster. So that's the reason why the write operation have different latencies. This is so-called a non-deterministic write. So in order to overcome this non-deterministic write, phase change memory use iteration-based write algorithm. So at the very beginning, it has a reset operation, very short and large amplitude current reset operation to generate this morpher fraction. And then it issues set pulses between two pulses, there is a verification operation. The operation, this verification operation will check whether the resistance reach the target resistance. So whether you have a good enough filaments to represent your current resistance. If yes, it will stop. Otherwise, it will continue to do the, verify, set iterations until it reach target resistance. So we actually need to write more to the cell, to each cell. We have to pay more power because we have more writes. We will hurt the endurance of the cell because we write more. Why do we need to write 2 bits in one cell? The answer is simple. Because the historical price for your storage in terms of megabytes significantly decreases with age. So we actually pay more attention on the cost per bit. For example, let me use your flash drive as one example. For example, when you have your USB flash drive, you don't actually care whether it can be written by 50K times or 5,000 times, because most of the time you just maybe for 1 year you just write it 100 times. You pay less attention on the endurance, on the reliability. What you are hoping now is that you can write more. You prefer, let's say, 4 terabytes USB compared to maybe only 1 terabyte USB, because sometimes you just need to, do the backup for your entire file system. So in this way, you prefer a larger one. So this is the reason why I cannot say everybody prefer multiple level cell, but most of us prefer multiple level cell. If you clearly know that you are frequently write that flash drive, then you can buy some specialized flash drive, which has a smaller capacity, but can tolerate more writes, can have a better reliability. So in this talk, I will introduce 3 problems on the PCM. One is the long write endurance. Second is the short endurance problem. And the last one is the write power. And this is the first problem, the long latency. So we have the PCM cell here. Each cell can record more than 1 bit, 2 bits in this example. And this is the data we want to write in the cell. Because of the reliability issue, the short endurance problem, we want to write less to each cell so that a cell can stand for a longer time. We need to avoid unnecessary writes to each cell. What we can do is that we just read the content of the cell and then compare the content in the cell against the content we want to write into the cell. So if they are the same, then we just skip that cell. Otherwise, we just write the new content. In this example, we have one cell stays the same, and we need to change for the other cells. We do a reset operation. We just follow the right algorithm, do the reset, and then set. Again, we write different contents. We need to generate a different amount of crystalline filaments on the Morpher fraction. So if the growth path of your crystalline filaments has more antimony, then basically you are faster. This write operation can be faster. You use a less iteration of writes, then you can finish earlier. And then for some unlucky guy, it has very little antimony, then it will take longer time to finish the write. So eventually, only a very small portion of cell will have these cases. We call it a difficult to write cell. So if we can stop the write operation earlier on these difficult to write cell, then we can reduce the write latency. In this particular example, we can reduce the write latency for the entire line by 50%. So let me summarize the situation a little bit. So we need to write the cell. Some cell is difficult to write because of the non-deterministic write problem. And the cell, the difficult to write cell can be the cell 2 in this figure. So in order to stop the write operation on the cell 2 earlier, we can treat the write, non-pending writes or unfinished write as a error. Then we can just stop anyway. We don't need to care whether we write the cell successfully or not. We just stop and treat it as an error. Then we can use ECC to correct the error in this example. Then we can stop earlier. And of course, we need to write ECC. Then we can, relax the constraint on the write operation. Now, we don't have to wait all the cell reach the target resistance. We can stop earlier if the ECC can cover all the errors now. Because the non-deterministic write, sometimes, so for one time, maybe the cell 2 is a difficult to write cell. For other times, maybe the cell 126 is a difficult to write cell. All because of these non-deterministic write and the distribution of your antimony. So eventually, maybe the ECC can also have the difficult to write cell. It doesn't matter because the ECC can cover all the errors within this range. So the ECC can take care of itself. If unfortunately you have too difficult to write cell, at this time we have to wait until one cell finishes write, and we can use the ECC to cover the most difficult to write cell. If you want to cover two cells, then you need to have a longer ECC. So this is trade-off. If you want to have faster writes, maybe stop much earlier than this, like at this time point. If you want to stop, then you have to more stronger ECC. So by this simple technique, we can reduce the latency by 50%, almost 50%. We can achieve some speed up on the overall performance. Another problem is that now, including your flash drive and also the phase changer memory, the cell will be broken after a fixed number of writes. The previous work found that there is a huge impact introduced by the reset energy on the cell endurance. So if I double the reset energy, then the cell will be broken much earlier. the cell lifetime is reduced by maybe 99% in this case. So this is the right algorithm, iteration-based right algorithm. And this is single level cell case, which we can record only 1 bit. This is a multiple level cell. In all the types of cell, in both the types of cell, no matter it's a single level cell or multiple level cell, we need a reset anyway to initialize the cell to the maximum resistance it needs. For the single level cell, because we only have 2 states here, it has a smaller maximum resistance. So we can use a very small reset energy to do the reset operation. But for the multiple level cell, we need a large range to tolerate more states. We need a larger maximum resistance. Then we need a larger reset energy to do that. This is the reason why multiple level cell has less lifetime compared to the single level cell. So the multiple level cell will be broken earlier than the multiple level than the single level cell. Assume that you have the same write traffic and write pattern. So the reset operation here actually is the critical factor to influence your endurance or lifetime of your single level cell and multiple level cell. So from the perspective of longer endurance or better reliability, we prefer a smaller reset energy. Only a smaller reset energy like this can help you to improve the reset. I can help you improve the lifetime. So clearly we have a so-called trade-off here. Either we can use multiple level cell, then we double the capacity for free, but we need to write a larger maximum resistance. We need to use a larger reset energy. The cell endurance is lower. Or we can have a single level cell. We do not care about your capacity. We can use, let's say, 50% of the capacity. That's good. And we can frequently write the cell. The cell will use a much smaller reset energy to achieve a much longer endurance. This is the trade-off here. Larger capacity. This is a larger capacity. Longer endurance, the second case. We can choose one. So how about, to explore this trade-off better? How about if we have a triple level cells? For the triple level cells, in the perspective of endurance, because we have a smaller maximum resistance, of course, you will have a longer endurance compared to the 2-bit multiple level cell. And compared to single level cell, of course, your endurance will be lower, will be shorter. But unfortunately, by 3 states here, you can still record 1 bit. It's impossible to record 2 bits because indicating 2 bits, you need 4 states, 2 to n. N is the bit number you want to represent. The data bit number you want to represent by these. So although the triple level cell is a simple, we cannot to enlarge its capacity. We cannot take advantage of this 1 extra state. Then one simple idea is that in order to, we can use double cell to record 3 bits. In order to record 3 bits, we need 2 to 3, which is 8 states. one cell has a 3 states, 2 cell has a 9 states in this case. So this is good enough. We can easily use a truth table to represent that. For example, if the first cell is a 00, the second cell is 00, then the 3 bits are triple zeros. If the first cell is a 01, the second cell is a 1x, then the 3 bits are all ones. 1x is the, is this cell, I'm sorry, the 1x is actually this state. When you have a 3 states, you can call it a 0, 0 or 0, 1 and 1x. This is you can call it this one 0, 0, 1x and 0, 1. You just can assign the 3 different names to 3 different states. In any combination, it doesn't matter. You just need a 2 cell to represent 9 states. Then now by the triple level cell in the memory system, we can have 3 different cells. We can apply compression, which is an algorithm to help you to reduce the data size. So we apply compression on each memory line. This is the size of the memory line. If this line can be compressed within this range, we store the cell in multiple level cell. This range indicates my data is not highly compressible, because you only reduce, let's say, maybe less than 30% of the size. By this non-compressible, not a highly compressible data, we can use multiple level cell, because multiple level cell has a larger capacity, can record more data. Well, if your data is more compressible, then we can use the triple level cell. If your data is highly compressible, it can be reduced to the less than 50% of your original data, then we can use a single level cell. So by different compression ratio, we can store data in different types of cells. And we found that most application actually has a lot of this case. The case where you can use triple level cell. So when, for example, if your original data is this much, and this is your compression ratio, after the compression, you have this much data. You can have a different option to store the data. The first one is still use the multiple level cell. And this is your memory line. Because your data is actually, because of the compression, your data is smaller than the cell you need actually is less than the number of multiple level cells. So you only occupy a portion of the line. Then you can rotate your data on this line, so that you can give some opportunity to these idle, to each cell, a idle opportunity to have a rest. So in this way, the cells in this line can be broken evenly, can be very evenly, so that at some time point, the entire line will be gone. You don't want to heavily use the first portion like this. In this case, these lines will be broken, of course, very fast. And then these lines are super good. These cells are super good. You don't want to have this case. You want to do a little bit of rotate. so that each cell in this line can be evenly broken. So in this case, because you always have a 30% opportunity to give the cell, 30% of the cell to have a rest, then you can improve the lifetime by 30%. After you compress the cell to its 70% size, original size, you can rewrite 25% of the compressed data as a single level cell, and the other 50% as a multiple level cell, like this. And of course, the multiple level cell will die earlier, much earlier than the single level cell. And you can also do the rotate like this. Because you only use 50% cell as a multiple level cell, then you actually improve the lifetime by double the lifetime, improve it by 100%. Or you can use the triple level cell. By triple level cell, you don't need to do rotate anymore because you just use up all the cells. And you also prolong the lifetime of each cell because you have a shorter reset energy, smaller reset energy on each cell. So this is the best case you can achieve. When you want to extend the lifetime of one memory line, you need to solve the worst case. So in the first case, in the first row here, the worst case is a multiple level cell. In the second row of this table, the worst case is still a multiple level cell. But in the last row, we just promote the worst case to a triple level cell. Because we can improve this worst case, then we can improve the lifetime of the entire line. We reduce the reset energy by 16%, and we improve the lifetime by 32 times. And then the last problem is the large write power consumption. This is the write energy and write latency figure. The set operation requires a long duration but a small amplitude current. The reset current uses a short duration but a large amplitude current. However, both of them are actually higher than VDD. Now the VDD is a 0.9, 1 volt or 1 volt. But even if I can provide you a 1.8 volt, by some tricks, the set and the reset voltage is much higher than this VDD. So in the current memory system, they use a charge pump to boost the voltage to the target resistance, to the target voltage. I'm sorry. So the structure of the charge pump is very simple. You just have a capacitor and a transistor. The charge pump has multiple stages. Each stage is very simple. You have a transistor and a capacitor. It's even similar to the DRAM. And then by switch on and off these transistors, you can actually pump the voltage up. You accumulate some charges here and then send the charges to the next stage and then the next stage, stage by stage. Eventually, you will have a higher voltage. This is what happened in this figure. So you can see that the pump is actually very significant in each PCM chip. It occupies 15% the chip area. So we call the output of the pump as the dynamic power. These are the useful power because we use the output power to do the reset, to do the set. And we call the power the pump get from the power source as the input power, which of course is the total power. And there is a difference between the input power and the output power here. The difference is actually the power overhead consumed by the pump itself. In order to elevate the target voltage, the pump itself needs to consume some power. Unfortunately, the power consumed by the pump itself is much larger than the output power. If I use the dynamic power divided by the total power, the power efficiency is actually only 50%. So in best case, 50% power is actually consumed by the pump itself. Then this is a problem. So let's break down the operation of the chip here: reset, set, and read, and the other things. You can see that the reset charge pump actually is the power bottleneck of the chip, and most of the energy or power is actually consumed by the reset charge pump itself. Why? Because reset require a higher target output voltage here. The higher target output voltage a charge pump needs to provide, the higher power consumption it will consume. So this is the reason why we have these useless overhead. We have to pay this overhead, but it actually, have no influence to our rights. So our goal is to remove this, eliminate this waste power overhead. Because the reset has a higher voltage, output voltage, this is the reason why the reset charge pump is more waste more power than the set charge pump here. So this is our goal. So let's review the right operation. Because we are writing different numbers represented by different resistance. Some resistance require more filaments. Some resistance does not require any filaments. For example, 00. 00 just require a Morpher fraction. So you don't need to set it. On the contrary, some number just need more size. Yes, more size. And we also have the non-deterministic right problem. But generally, we know some number require more size than other numbers. And this is what will happen. At the beginning of the right, we do reset. Here we have a so-called power use peak power, reset peak power. In order to support this peak power, of course, the peak power is very large here. In order to support it, we need a very large reset charge pump. We can actually do some scheduling to solve the problem. We can delay some reset. So we can reduce the peak power like this. We can delay the reset on the cells, on the numbers who will need a smaller number of sets, because these sets are not on the critical path. Anyway, this one is on the critical path. If we delay it we will prolong the write latency of the entire write operation. However, if we delay these resets, everything can be finished within the original latency. And we also can reduce the peak power here. So in this way, we can reduce the size of reset checkpoint for free without prolonging the latency. We can reduce the 70% size of the reset checkpoint without huge performance overhead. So in this talk, I introduce how, particularly in my group, what my group have done on the phase-changing memory part. We reduce the long write latency, we prolong the short cell endurance, and we reduce the large write power. Any question? So let's see. If no question, I will talk about the schedule. So I hope you can see the syllabus on my screen. So originally I want everyone to do the final presentation on 20. But I received some email to ask for extension. So now you can do the final presentation on 20 and 25. So now we finished the NVM in this lecture. So in the other class of this week, I will talk about assembly language. And then next week you can prepare your final presentation. Any question? If you have any question, any concern, just email me. Again, this is a graduate class and it's an introduction class. I hope you can learn something and do something which are useful for your current research or the job hunting. We have no written examination, just some projects. And if you have any question about this, please email me. Thank you very much. Otherwise, we can just stop. Thank you.